Today we will be using the Laplace transform to actually solve problems. Let's get this up. Okay, yeah, last time we saw what the Laplace transform is, a few examples of computing it, and that it's a linear operator. And so today we'll talk about how we can use it to solve initial value problems. So in order to do this, I'm going to set up a relationship between the derivative of a function and the Laplace transform of the function. So let's start off with a function. So we have the n. So the derivative f prime of a function f. And what we'll do is we'll try to compute the Laplace transform of this f prime. So we'll start off with the integral from 0 to a of e to the minus st f prime of t. So we're going to assume we're going to add in assumptions as we go on. So the first assumption I'm going to make is that f prime is piecewise continuous. So it's at least piecewise continuous. So that tells me that I can take this integral. So this is the integral that I would use for the Laplace transform. This would give me the Laplace transform if I took a to infinity. And I can write this as, well, since it's piecewise continuous, I'll just integrate the pieces. So from 0 to t1, e to the minus st, f prime of t dt, plus integral from t1 to t2, e to the minus st, f prime of t dt, plus, and so on, up to tn minus 1 a, the integral from tn minus 1 to a, of e to the minus st, f prime of t. So this is just splitting it up as along its pieces, piecewise continuous, we're assuming. And now we can solve each of these, or we can integrate each of these, perform each of these integrals by using integration by parts. So for that, the thing that I'm going to integrate is obviously going to be f prime. So the thing I'll take the derivative of, u, will be e to the minus st, and dv will be f prime of t dt. So for each of the integrands, in these cases are the same. It's just the limits of integration that change. So du will be minus s e to the minus st dt. And v, of course, will be f of t. So to write this out, I'm going to first collect together. Let me box this off by itself so that it doesn't run into the other stuff we're writing. I'm going to collect together the UVs. So our formula for integration by parts starts off with the UV evaluated at the points. So I'll have e to the minus st f prime of t, evaluated at 0, t1, plus e to the minus st f prime of t, evaluated at t1 and t2, and so on, up to e to the minus st f prime of t, evaluated at tn minus 1 a. Now I'll subtract from this the integrals v du. So I'll group all these together as well. And what I get is, well, I'm going to factor out this minus s from all of them. So I'm subtracting that, so I get a plus s times integral from 0 to t1. And then in this case, v du is e to the minus st ft. That minus s right here has been factored out to the front. So I just get all of these in. t1, t2, e to the minus st ft, dt, and so on up to tn minus 1 a, e to the minus st ft. So first, looking at the UV parts. So when I evaluate these at the upper limit and lower limit, what I'm going to get is, well, instead of writing that e to the minus st f prime of t over and over again, I'm just going to represent it as a box. So what I'm going to have is the box evaluated at t minus 1 minus the box evaluated at 0, right? Actually, let's do this in another color so we don't get it mixed up. Right, so that will be this first one right here. The second one will be T2 minus T1, and then the next one will be T3 minus T2, and so on. And you'll notice that there's a lot of cancellation that happens here. So this plus T1 and minus T1 cancel out. This plus T2 and minus T2 cancel out. This plus T3 will eventually cancel out with something, a minus T3 that appears later, all the way until we get down to Tn minus 1, sorry, A minus Tn minus 1. So what we get when we plug in A minus what we get when we plug in Tn minus 1. Now this Tn minus 1, of course, will cancel with the something appearing before it. And what we'll get out of all of this is just the 0 and just the A. All of these other ones will go away, canceling out like a telescoping series. So what we'll get is e to the minus s a f prime of a Oh, I apologize. It wouldn't be a lecture without me making a mistake. The V's are not F primes. They're F's. My mistake. There we go. So this is what we should have. E to the minus SA F of A minus what we get when we plug in 0 So e to the minus s times 0 will just be e to the 0, which is 1. And then so we get just f of 0. Okay, so that's this part taken care of. Now this next part, we're going to make another assumption. We're going to assume f is continuous. So we've assumed that f prime is piecewise continuous. F is continuous. Well, if f is continuous, then when we take the integral of all of the pieces, that's the same thing as just taking the integral of the whole function. So we get is plus s times the integral from 0 to a, e to the minus st, f t, dt. And just to recall, the left-hand side of this thing was the integral from 0 to a of e to the minus st, f prime of t, dt. So I've scrolled it off the screen at this point. Okay. So taking the limit as a goes to infinity on both sides, I get the limit as a goes to infinity. This was originally our left-hand side. I'm going to move it back to the left-hand side, just for the sake of it looking. E to the minus st f prime of t dt. This will just be the Laplace transform of f prime, right? Now, let's figure out what the right-hand side here should be. Sometimes the highlighter goes behind the font, sometimes it goes in front of the font. Anyway, so in order to compute this, we're going to make one more assumption. We want to know something about, well, we need to know one more thing about this f. We want to know that it's of exponential order. Specifically, we're going to say that f of t is bounded above by k e to the at. So it's bounded by this exponential multiplied by some arbitrary constant. Or what should I say? When t is greater than or equal to capital M. So it's eventually bounded by this e to the at. As we go to large enough t, eventually this evens out to be bounded by an exponential with growth rate a. So what this tells us is that f is continuous, so it's at least piecewise continuous, a fortiori. And it's of exponential order with the growth rate a, and so the Laplace transform of f exists for s greater than a, or the real part of s greater than a. So that tells us a couple of things. First of all, this e to the minus sa f of a, this absolute value, well, e to the minus, write it like this. Come on. I am erasing. E to the minus st f of t is bounded by, well, f of t is bounded by an exponential, so this is just bounded by another exponential. So it's bounded by this one when t is sufficiently large. And because we are assuming that s is greater than a, because that's where we're going to be looking for this Laplace transform. E to the minus st f of t goes to 0 as t goes to infinity. Right. Since s is greater than a, this e to the minus s minus a is going to be e with a negative growth rate, so it's going to have a decay rate. It's going to decay exponentially. So it's going to go towards 0 as its parameter goes to, or its independent variable goes to infinity. And so this part right here, this thing, goes to 0 as a goes to infinity. So that's 0. This thing right here is, like we said before, the Laplace transform, which exists. So we have S, the Laplace transform of f, minus f of 0. So we've established a relationship between the Laplace transform of a derivative and the Laplace transform of the original function. Very nice. Now, we can use this if we want to compute the Laplace transform of the second derivative. And we can do this just by chaining together two applications of this rule that we've come up with. So this will be the Laplace transform of S. This Laplace transform will be S times the Laplace transform of f prime minus f prime at 0. And this is just S times this quantity, S times the Laplace transform of f minus f of 0 minus f prime 0. So this is S squared Laplace transform of f minus S times f of 0 minus prime of 0. And we can continue this process to get the Laplace transforms of higher derivatives as well. So instead of working through another example of that, we'll just collect together this idea in a theorem. The proof will be just apply it as many times as you need to. So let's suppose all of our assumptions that f, the nth derivative of, well, let's just say f derivative f, the second derivative of f, all the way up to the n minus 1th derivative of f. All of these are continuous. And that the nth derivative, the highest derivative that we're looking for, is piecewise continuous. Right? We only needed that this thing was piecewise continuous. It doesn't even have to be continuous. So suppose all of the lower order derivatives are continuous. The highest one is piecewise continuous on any interval from 0 to a. So making a arbitrarily large if we need to. We will need to. And that the function is bounded by an exponential. It's of exponential order. The derivative is of exponential order all the way up to the n minus 1 derivative. So all of these things are continuous and of exponential order. And then the thing that we're trying to compute the Laplace transform of is just piecewise continuous. This is that condition. It says it's bounded by an exponential eventually. Okay. So all of these are continuous. They're all of exponential order. And then the one we're trying to find the Laplace transform of is piecewise continuous. Then the Laplace transform of the nth derivative exists for s greater than a, or in the complex plane, the real part of s is greater than a. And we have a formula. The Laplace transform of the nth derivative of f. This is equal to s to the n times the Laplace transform of f minus s to the n minus 1. So the exponent goes down by 1. F of 0 minus s to the n minus 2. F prime of 0 minus, and of course, it continues like this, getting all the way down to s times the n minus 2 derivative evaluated at 0 minus f the n minus 1th derivative evaluated at 0. So just by continued application of this rule that we've already. Okay. So this gives us the connection between all of these things right here constitute the initial value of our solution. And so this gives us a connection between the initial value and the Laplace transform of the solution. So what happens when we actually apply this to a problem? I'm going to write up an example. Y double prime minus y prime minus 2y equals 0. There's our ODE, homogeneous, second order, linear, constant coefficients. And this is our initial condition. Okay. This is a problem that we actually already know how to solve. We don't need the Laplace transform for this. So I'm going to take a break to give you a chance to solve this using the tools that you already know. This is like a pop quiz, but you get no credit for it. And I'll return whenever you're done. Are you ready for me to work it out? So this one, I mean, we've seen problems like this over and over. We can compute this by getting the characteristic equation, which is r squared minus r minus 2, which factors as r minus 2, r plus 1. And so we get r1 equal to 2, r2 is equal to negative 1. And our general solution is c1 e to the 2t plus c2 e to the minus t. Cool. Now, if we plug in our initial conditions, we get c1 e to the 0 plus c2 e to the 0 equals 1. And 2c1 e to the 0 minus c2 e to the 0 is equal to 0. So in other words, c1 plus c2 equals 1. 2c1 minus c2 is equal to 0. If I add these together, I get 3c1 is equal to 1. I get c1 is 1/3. And then using this equation right here, I can figure out that c2 has to be equal to 2/3. So what I get is that the specific solution is 1/3 e to the 2t plus 2/3 e to the minus t. Okay, no sweat. We've seen this one many times. This is something that we can do. Now let's. I was going to say unnecessarily complicate things, but it is necessary. We have to use this Laplace transform at some point. So let's solve this using the Laplace transform. The way that I do this is that I'm going to take the Laplace transform of both sides. So that is L applied to y double prime minus y prime minus 2y. If I do the same thing to both sides, it's got to be the same result. Okay. Now, using linearity, I can rewrite the left-hand side as the Laplace transform of y double prime minus the Laplace transform of y prime minus 2 times the Laplace transform y. Now, we didn't talk about what the Laplace transform of 0 is, but you can guess at what it would be. Integral from 0 to infinity of e to the minus st times 0 dt is just the integral of 0. So this will be 0. Our right hand side is just 0. Now, let's use our newly created theorem to figure out what the Laplace transforms of each of these derivatives are. Oh, I want to copy down, do it like this. y0 equal to 1, y0 prime. Because I'm going to scroll them off the screen. I don't want to lose them. All right. So this first one is s squared times the Laplace transform of y. Now I'm going to switch to just writing capital Y at this point. As much as I enjoy writing these fancy L's, I'm not going to do that. Minus s times y0 minus y prime 0. Right? Minus the Laplace transform of y prime, which is s capital Y minus y0 minus 2 times the Laplace transform of y, that's just y. Now I will collect together all of the y's to get s squared minus s minus 2 times y. So that is this one, and this one. And then minus s times y0. Well, y0 is 1. So minus s minus y prime 0. That's just 0. And then minus y0. That's plus 1. And this is all equal to 0. Still everything's equal. Now I'm going to take all of the non-y. This is just an algebraic expression now, right? We're just solving for y, capital Y. So I move all of this non-y stuff over the other side, and I get, sorry, what? Give me a second. They always tell you that all of this educational technology is really important because it makes all of these tasks that you have to do so much easier. But every time you introduce something new, it's just one more thing that'll break. Okay. So moving the non-s stuff over the other side, I get s squared minus s minus 2 y. I'm not anti-technology. I'm just anti having my time wasted. That's all. On the other side, s minus 1. Okay, now divide both sides by that stuff. And we get capital Y. Now, the question becomes, can we find Y so that the Laplace transform of Y is equal to s minus 1 over s squared minus s minus 2? Question mark, exclamation mark. Obviously, the answer is yes, because we've already solved this problem. We already know the answer. But let's pretend that we don't. It's nice that we know the answer because we can compare it to something in a minute. Well, if we remember from yesterday, we had the Laplace transform of e to the AT, and this was equal to 1 over s minus a. That was very nice. That's kind of looks like a fraction, like this thing. And we also know that this is equal to s minus 1 over, we know how to factor s squared minus 2s, s minus 2 times s plus 1. So maybe we can break this thing apart so that the denominators are just in the form s minus a. The numerators, well, that's totally fine. We can just, if we can get those to be constants, then using linearity, we can pull that out. Well, of course, we already know a technique for doing this, and that is partial fraction decomposition. So if we set this fraction, s minus 1 over s minus 2 times s plus 1 equal to a over s minus 2 plus b over s plus 1. Then we can solve this thing using partial fraction decomposition. And no, this is partial fraction decomposition. We can solve this thing. Well, there's lots of different methods. You had taken my Calc 2 class, you were in that class, and you would have seen maybe 3 different methods that we can use to solve this thing. But I'll just use the traditional one of clearing denominators. So if we clear denominators, we get s minus 1 equals a times the s minus 2's cancel out, and we get plus 1 plus, let's just show all of the work here. We're multiplying both sides by s minus 2 times s plus 1. Okay. That's clearing denominators. We're multiplying by the least common multiple of all the denominators. So all of this cancels out. The s minus 2's cancel out here. The s plus 1's cancel out. So what we're left with is s minus 1 equals a times s plus 1 plus b times s minus 2. And that is as plus a plus bs minus 2b. So that's a plus b times s, and then plus a minus 2b. Right. Okay, and now we've got a system of linear equations where we have a plus b is equal to 1. That looks familiar. And then a minus 2b is equal to negative 1. Or we could write that as 2b minus a is equal to 1. Makes it a little easier to add these things together. When we add them together, we get 3b is equal to 2. So b is 2/3. A is 1/3, just a single third. And what I get is that y is equal to a over s minus 2, yeah, plus b over s plus 1. And so what I get from this is that y is equal to, well, exactly what we would need if we were trying to get this as our y. 1/3 times e to the 2t, because when we take the Laplace transform of that, we'll get 1/3 times 1 over s minus 2. And the same thing for 2/3 e to the minus t. Of course, we get the same solution. Okay. Now, there was nothing special about all the numbers that we used. We can do this for the arbitrary linear ODE, the general linear ODE with constant coefficients, and we can even have a non-homogeneous term. So what happens? Well, the general form of this is ay double prime plus by prime plus cy equals f, where f is a lowercase f. So f here is a function of t. If I take the Laplace transform of both sides, I get a times s squared y plus, I should write out our initial condition. Right, arbitrary y0 and y0. So I have a times s squared y plus s y0 plus y prime 0 plus b times sy plus y0 plus cy equals, and then for the Laplace transform of little f, I'm going to write big F. Okay. Now collecting y's together, I get as squared plus bs plus cy. And then all the other stuff, well, let's collect, what should we collect together? Let's collect together the y zeros. As plus b minus 0, and then a y prime 0 with capital F. I've done nothing but rearrange this point. Now we'll move all the non-y stuff over to the other side. You know what I'm going to do. I'm going to divide by that stuff. So let's just do it all in one step. F minus AS plus B minus 0. Oh, sorry. Yep. These should be minuses. The way I typically remember that, or the way I have in the past, because I haven't looked at the Laplace transform in about 8 years before yesterday, was that whenever you do the definite integral, you end up with an evaluation at the upper and lower limits. So the upper limit minus the lower limit. There's kind of an analogy going on here between this being the upper limit has the y, and then the lower limit has all of the initial conditions. So that's one way to kind of remember that is by analogy. Of course, that doesn't help if the analogy fails you, like it did me just now. But hey, at least it exists. So we solve for y and we get something, I mean, this is an algebraic problem. We get something just completely in terms of s, where of course this capital F is a function of s. Right. So that brings us to a couple of points to think about for these using the Laplace transform to solve these problems. First point, the Laplace transform takes a differential problem and turns it into what we rightly think of as an easier algebraic problem. Right, this was something that we could solve just using addition, subtraction, multiplication, and division. So that's really powerful. Now we're left with the problem going back in the other direction. We'll come to that in just a second. The second thing to note is that our specific solution is automatic. In other words, what IE stands for, in other words. In other words, there's no intermediate step of finding a general solution. They might argue with me and say, well, we did have a situation where we found some arbitrary coefficients and we solved for them in that partial fraction decomposition. Okay, that's fair, but there's other ways to solve partial fraction decomposition that are more direct. So really, that's an interesting thing about this Laplace transform is that it's very different from the ways that we've been solving problems so far. Completely skips this step of finding a general solution. Now, it doesn't find a general solution at all. We go straight to the specific solution, but actually a good thing in some ways. Now, returning to problem number 1, which is once we have y, how do we get little y. That's the thing that we really want. And I'll say in general, this is a hard thing to do. It's a difficult thing to do. Well, this is differential equations. We never get away from a difficult problem. We just shift the difficulty to some other area. We just kind of move it into a. It's always going to be difficult. Differential equations are intrinsically difficult problems. So this is where the difficulty comes up. Doing an algebraic thing is easy. There is a formula for an inverse Laplace transform. And I'll write it down only to dazzle you. Right. So it takes the thing in the frequency domain and turns it back into the time domain, the complex frequency domain. And so what's the formula for this? It's 1 over 2 pi I. You don't need to write this down. You're never going to use it. The limit as capital T goes to infinity of the integral of gamma plus I t, gamma plus I, gamma minus I t. E to the st f of s d, excuse me, ds. Okay. So we'll just briefly look at this, first of all, to see that this is not something that we're not going to do this. This involves complex variable calculus, which is not so bad. What you'll see here is that this upper and lower limits integration, this is just a vertical line. It's in the complex plane, but we've done integration over a line in the plane before. That was something that we did in 3, right? So it's not so far away from what we're used to. But it does involve understanding calculus of complex variables, which is not something that we cover in this class. That's a whole class unto itself. Also, we need to know something about this f of s. We need to know where all of its singularities are. So these are sort of like the places where it's not really well defined. This gamma, this line here, for real values of gamma, or x coordinate, if you think of that in the plane as gamma, it's going to be to the right of all of those singularities, and f of s has to be bounded on that entire line. Okay. Now, let's see, how much time do we have left? 9 minutes. We can try to squeeze the beginning of another problem in here. I just wanted to show you this, but also to show you that, again, this is just an integral. This is another integral transform. And so, you know, we know that the integral is a linear operator. And so we know that this inverse transform is going to be linear as well. We can apply linearity. Okay. Now we'll attempt another example. And actually, this is an example that another one that we already know how to do. We'll skip the step of doing it in the old way. I think we could use variation of parameter, or no, we could use variation of parameters. We could use method of undetermined coefficients for this, either or. To apply the Laplace transform, we need initial conditions. So the y of 0 is equal to 2, y prime of 0 is equal to 1. And so what do we do? Well, taking the Laplace transform of both sides, on the left-hand side, I will get s squared capital Y minus s times y of 0, which is 2, minus y prime of 0, which is 1. S times 2, I should write that as 2s. What am I thinking? Okay, and then plus y. Now, yesterday we figured out what the Laplace transform of sine of 2t will be. So the Laplace transform of sine of at was a over s squared plus, I don't know what a is, 2, over s squared plus a squared. Just checking my notes to make sure that's not wrong. Okay, now rearranging some stuff, what I will get is s squared plus 1 times y is equal to 2 over s squared plus 4 plus 2s plus 1. That's going to be a little bit of, let's go ahead and get common denominators. So this will be s squared plus 4 over s squared plus 4. So that's 2 plus 2s cubed plus s squared plus 8s plus 4 for s squared plus 4. And really all the collecting of like terms that I can do is adding this 2 to this 4. That's 6. And then dividing both sides by s squared plus 1, I get y is equal to, let me double check that. Yep, got it right. Okay, 2s cubed. That's the most exciting thing that's going to happen. S squared plus 4, s squared plus 1. And now, check the time to see if I can get out of doing this. No, I can't. This we will do partial fraction decomposition again. Now we can't factor these denominators anymore unless we start using complex numbers, which I'm just going to avoid because we don't have to. We can just factor it, or we can partition it as 2 different quadratics. So in the denominator for this one, we will have s squared plus 4. In the denominator for this one, we will have s squared plus 1. We're just going on muscle memory at this point. The numerators will have to be linears, general linears. So this will be ax plus b. Remember, the numerator has to be 1 degree lower, dx plus d. And so clearing denominators, I get 2s cubed plus s squared plus 8s plus 6 equals ax plus b times s squared plus 1 plus dx plus d s squared plus 4. Now distributing and collecting like terms. Okay. Well, let's do this all in one step. I'm going to get the cubics first. Maybe I should choose not to do the smart thing. I should choose to do the smart thing and use the right pair. There we go. Okay, so the cubics will be as times s squared, so that'll be a, and then cs times, I'm looking at it and I'm actually pointing at it, but you can't see what I'm pointing at. There we go. These are the cubics. So I'm going to get a plus c s cubed plus Let's see. What are our linears? AS times 1. No, so we need a quadratic. So B times S squared plus D times S squared plus, now our linears. So AS times 1 plus CS times 4. So A plus 4CS. And then finally our constants, B plus 4D. Okay. Still not out of time yet. Actually, let's just leave it at that for now. We're going to solve this thing using, well, let's look back. I should say, I have a table of Laplace transforms in front of me. Whenever you work problems like this, that's the way we'll do these things. We never compute the inverse Laplace transform ourselves. We always use some table. And so I'm using a table, and what I see is that sine of AT, we've already seen this one. This goes to A over S squared plus A squared. Now that'll give us our constant over a quadratic. So that's fine. But we want a linear over a quadratic as well, and that's cosine. So not equals, this is by the action of the Laplace operator. S over S squared plus A squared. And that should be enough to figure this out for us. So once we figure out what A is, we'll have AS over S squared plus 4 plus B over S squared plus 4. And then the same thing for CS plus D, right? We'll go through those steps. And then what we'll get is we want this thing to be some constant times A over S squared plus A squared, right? So we're going to have an A over 2 out in front. And this will go to, taking the inverse Laplace transform, A over 2 times sine of 2t. I'm sorry. I'm sorry. Yeah. Okay. A over S. This is going to go to A times cosine of 2t. This one is the one with the constant. So we want it to be B over 2 times 2 over S squared plus 2 squared. And this will go to B over 2 sine of 2t. The important thing is not that you don't make mistakes, it's that eventually. Okay. Anyway, you can finish that one off for yourself. If you've looked up the Boyce and DePrima book, which I do highly recommend that you do, any addition works. Calculus hasn't changed for 500 years. That's an exaggeration. More like 300 years. 200 years. I think this technique was sort of really built up maybe about 150 years ago, something like that. 150, 160, somewhere between 150. So anyway, the addition from last year isn't going to make a difference. So you can find an old edition online for free and look at that, and I highly recommend you do. There's another example that I didn't have time to work through, and there are also lots of good problems and no typos. The important part. Okay, I'm going to stop there for today, and I will see you hopefully tomorrow, unless you have questions, which I'll stick around.